All right, buckle up for this one, folks, because today we're going deep, really deep into something, well, kind of mind-bending. We're talking about a possible theory of everything.
Oh, yeah, that elusive holy grail physicists have been chasing, what, for centuries, right?
Exactly. You know, that one idea that could explain literally everything in the universe
From the tiniest little
to
atoms,
the vastest galaxies.
using just one elegant idea.
And that's what we're diving into today.
It's a tall order, for sure.
It is. It is. And the framework we're looking at, the one trying to pull this grand unification off, is called the Grand Fibonacci.
SMFRVS framework.
Now, I know that sounds like something straight out of, like, Star Trek or something, but
Yeah, it's got a certain ring to it, doesn't it?
trust us. Stick with us.
Mm-hmm.
This deep dive is all about understanding, well, how this theory even attempts to do what it claims, you know?
Yeah, it's really fascinating how it challenges, like, some really basic assumptions we have about the universe, like
Really?
gravity.
Gravity, what about it?
Well, the force that keeps us on the ground, planets in orbit, all that.
Yeah.
This theory says it might not be a pull at all.
Wait, what?
Yeah, it suggests gravity could actually be a push.
Hold on, you're saying the universe isn't just held together, it's being actively pushed outward.
That's the idea.
Whoa, okay, so tell me more about these,
Subtle magnetic fields.
yeah, those, and how they interact with this vacuum you mentioned.
Right, so the theory proposes that these subtle magnetic fields, or SMFs, are like everywhere, permeating the entire universe.
Okay.
But they don't exist in a void. They interact with what the theory calls the relative vacuum of space.
Which isn't really empty, right?
You got it. It's more like this dynamic, ever-changing field, kind of like,
Like a cosmic ocean.
exactly,
Yeah.
with these subtle ripples and waves constantly in motion.
Okay, so we've got these SMFs interacting with this not so empty vacuum.
Yeah.
But how does that create a push force that we experience as gravity?
Right. So the essay lays out the math pretty deep, but essentially it shows how these two elements, the SMFs and the RVS,
They work together.
yeah, they work together to create this force that pushes outward, not inward.
So instead of being pulled towards the Earth, we're being pushed towards it by this cosmic push force.
That's what this framework suggests.
That's wild. So this push force, it's not just for us sticking to the ground, right?
No, not at all. The theory says it's responsible for, like, the orbits of planets, the structure of galaxies, even the very structure of atoms themselves.
Wait. How does this push force explain how an atom is structured? I mean, atoms are tiny. We're talking about, like, galaxies here. The scales are completely different.
And that's where the Fibonacci part of the theory comes in. It uses something called Fibonacci fractal scaling.
Okay, fractals, I get that, like those cool patterns you see in nature, the branches of a tree or a coastline.
Right, exactly. This theory says the universe itself follows a similar fractal pattern. The same patterns repeat at different scales, from the smallest to the largest.
So you're saying the way planets are arranged in our solar system, that pattern could be mirrored in the structure of an atom.
That's the mind-blowing part.
That's crazy. Okay, so atoms, they have a nucleus, right? Made up of those protons and neutrons, and then electrons whizzing around them.
Yeah, and the Grand Fibonacci theory links the stability of those atoms to the number of protons and neutrons.
The magic numbers I vaguely remember from chemistry class.
Those are the ones.
But those magic numbers, they're not just some random thing, right?
Yeah.
There's a reason why certain configurations are more stable than others.
Absolutely. And the Grand Fibonacci theory explains it through the interaction of, you guessed it, those SMFs and the RVS.
Okay, so how do they fit in?
Imagine that this interaction creates specific spots, kind of like nodes, where particles can exist stably.
So these nodes, they're like preferred parking spots for particles within an atom, and the magic numbers tell us how many spots are available.
Exactly. It's like the universe has these preferred spots for particles to hang out, and these spots are determined by the fractal pattern created by the SMFs and the RVS.
So then, could stable elements in other parts of the universe be different from what we have here?
That's a really interesting implication of this framework. It suggests that maybe what's stable here on Earth might be unstable somewhere else, and vice versa.
So alien life could be based on chemistry we can't even imagine.
It really opens up the possibilities, doesn't it?
That's wild. And this is just the beginning of how the Grand Fibonacci theory challenges our understanding of the universe. There's so much more to explore. Alien life with total different chemistry, wow. Okay, but what about some of the other big mysteries out there, like black holes?
Oh, now black holes, that's where this theory gets really, really interesting. You see, The Grand Fibonacci framework, it kind of throws out the textbook on black holes and gives us a totally different perspective.
A different perspective. Huh. In what way?
Well, you know how we usually think about black holes? With that singularity in the center and all.
A singularity, that's what, like a point where everything gets crushed into like infinite density.
Exactly. And that idea, that's mostly based on like Einstein's theory of general relativity.
Einstein, okay.
But the problem is this whole singularity thing, it clashes like big time with some of the core principles of quantum mechanics.
Quantum mechanics, that's the weird stuff.
Oh,
right?
it's super weird. And it leads to this thing called the black hole information paradox.
Information paradox. That sounds intense. What's that all about?
It's a huge question, really. It asks, like, what happens to the information that was in the stuff that falls into a black hole? Like, is it gone forever? Boof.
That does seem like kind of a big deal, yeah.
It is. And this is where the Grand Fibonacci framework swoops in and says, hold on, maybe there's no singularity at all.
No singularity, but how?
Remember that outward push we talked about from the SMFs and the RVS?
Yeah, the whole push gravity thing.
Right. So as a star collapses in on itself to form a black hole, that push force gets crazy strong, but it's not infinite.
So there's a limit. It doesn't just keep crushing down forever.
Yep. The star's core, it doesn't become a singularity. Instead, it gets super, super dense, but it's still finite.
So if there's no singularity, no information paradox.
Potentially, yeah. The theory says the information could get, like, encoded in this super dense core, and it could maybe even leak back out into the universe through things like Hawking radiation.
Hawking radiation is like black holes glowing.
You got it. And this whole solution, it fits perfectly with that push-based model, right?
So we're saying this theory might just bridge the gap between like general relativity and quantum mechanics without inventing some whole new physics.
That's what makes it so compelling. And this push force, it might explain even more than just black holes. Think about the Big Bang. The Grand Fibonacci framework, it takes that same fractal principle and applies it to the very beginning of the universe.
So no infinitely small point, no singularity at the moment of creation. What does it say happened?
Instead of a singularity, imagine the universe starting as this tiny but finite thing, already buzzing with that SMF-RVS interaction and that fractal scaling we've been talking about.
So the universe expands from something small, but not infinitely small.
Exactly. But then wouldn't that mean the universe is always expanding?
Well, it is expanding, and actually it's expanding faster and faster all the time.
And that brings us to another mind-blowing implication. See, this outward push from the SMF-RVS interaction, it could be the reason the universe's expansion is accelerating.
Hold on, are you saying the same force that gives us gravity, black holes, atoms is also pushing the entire universe outward?
That's the idea. It's a single force acting differently at different scales because of this fractal principle.
Wow, this is really living up to the name theory of everything, huh?
And we're not done yet. The essay even goes on to address those weird, huge magnetic fields we see in space.
Oh yeah, I've always wondered about those. You know, these massive magnetic fields stretching across galaxies, where do they come from?
Well, remember how we said that SMFs are, like, baked into the universe from the get-go?
Right, they're fundamental.
So as the universe expands, those SMFs interacting with that RVS, they shape and amplify those early magnetic fields, eventually forming those huge structures we see today.
So no need for some other crazy explanation. The magnetic fields are just a natural outcome of the SMFs from the very beginning.
That's the beauty of it. No extra stuff needed. It all just flows from the initial conditions. And that leads us to something truly mind-boggling.
Okay, you've got me hooked. Gravity, black holes, the Big Bang, expansion. What else could there be?
The essay mentions something called multiversal chemistry. And if you thought the stuff we've talked about so far was wild, buckle up.
Multiversal chemistry. I'm all ears.
Think back to those different star systems we were talking about. Each one has its own unique layout of planets.
Right, so different fractal patterns from the SMFs and the RVS.
Exactly. And what if those different patterns also affect which elements are stable? What if those magic numbers we discussed, those stable atomic configurations, they change from star system to star system?
Hold on, you're saying the periodic table, something we think of as fundamental to chemistry, could be totally different somewhere else in the universe?
That's one of the incredible possibilities the Grand Fibonacci framework suggests. Those elements we think of as stable here on Earth, they might be totally unstable in other star systems. Imagine a universe where every star system has its own unique set of stable elements.
So different types of chemistry, different planets, maybe even different kinds of life.
Exactly. And it all hints at the possibility that maybe, just maybe, there's one equation, a golden equation, that describes all of this. An equation that captures the interaction of SMFs and the RVS, the fractal scaling, and those node conditions.
One equation to explain everything. That's a pretty ambitious goal.
Yeah.
But if this theory is right, it would be a complete game changer.
It really would, and it would be a huge testament to the human drive to understand the universe.
We started with tiny particles, and now we're talking about the whole universe, black holes, the Big Bang, even the idea of a multiverse with different chemistry. It's amazing how it all ties together.
It's the elegance of a potential theory of everything, isn't it? Finding that underlying order, connecting all these different things we see.
But we do need to remember, this is all still just a hypothesis, right?
Absolutely. And even if the Grand Fibonacci framework turns out to be, not completely right, it still gives us a new way to think about the universe and all its mysteries.
It definitely gives us a lot to ponder.
Makes you wonder what else we might have wrong, right?
Totally. But as cool as this all sounds, we got to be real, this Grand Fibonacci theory, it's still a hypothesis.
Yeah.
Needs some serious testing.
Oh, for sure. For sure. But the great thing is, this framework, it makes some pretty specific predictions that we can actually go out and investigate.
Like what?
Like those super heavy elements. Remember those magic numbers that are like way beyond what we've ever seen?
Yeah, those super heavy ones.
If we could find those, that would be huge.
So finding those elements would be like proof of this whole theory.
Well, it would be a really strong piece of evidence, that's for sure. Finding those elements with those magic numbers like 108, 114, especially 164.
What's so special about 164?
That's the big one. That's the final element in this framework, the theoretical limit.
The end of the periodic table.
It would really support this whole idea of fractal scaling and nodes determining stability. And it's not just about making them in a lab. The theory also says that these super heavy elements, they might actually exist out there in the universe in like really extreme environments.
So we got to keep looking, both here and out in space.
Exactly. And there's another place we can test this theory, planetary rings. The essay, it suggests that those rings, they're like subnodes within the bigger fractal pattern of a solar system.
Hold on. So if we look at like Saturn's rings and we see fractal patterns,
Especially if we see those patterns repeating at different scales.
that would be another point for the Grand Fibonacci framework.
Absolutely. It would be like seeing that interconnectedness that the theory's all about, playing out right in front of us.
Mind-blowing to think that something as, I don't know, as beautiful as a planetary ring could help us understand the universe's biggest secrets.
It is pretty amazing, right? It just shows you how much we still have to learn. Every time we find something new, it opens up a whole new world of possibilities.
Makes you wonder if we're just scratching the surface of what's really out there.
It does, it does. And, if this Grand Fibonacci theory turns out to be even partly true, well, it changes everything.
It would completely reshape our understanding of the universe, that's for sure.
And not just the universe, but our place in it,
Yeah.
It really makes you think about the big questions, like what is reality, really?
Okay, so wrapping up, what should people take away from this deep dive?
I think the biggest thing is to never stop questioning, to keep exploring new ideas. Don't just take our word for it. Go out there and research, dig deeper, see if this resonates with you.
Yeah, we've just touched on some of the main points of this crazy theory. There's a whole universe of information out there waiting to be discovered.
That's right. Keep learning, keep those questions coming, and most importantly, keep an open mind. We're living in a pretty exciting time for science.
Definitely. Who knows what kind of mind-blowing discoveries are just around the corner. Thanks for joining us on this deep dive.